In this lecture, we will talk about maximum power transfer to a load using phasor domain analysis techniques. Okay. So consider the case that we have a load that's part of a circuit in sinusoidal steady state, an LTI circuit in sinusoidal steady state. Therefore, our load can be represented by its impedance. And also, the circuit that is connected to can be represented by the Thevenin equivalent circuit. So, as far as the power transfer problem is concerned, we can work with the following simple circuit. Okay. So here on the left hand side, we have a voltage source connected in series with an impedance, so that would represent the Thevenin equivalent circuit, seen by the load, and then here we have the impedance representing our load. Okay, ZL is RL plus J XL. That's our load, and this here to the left of this dashed line is the Thevenin equivalent circuit as seen by the load. Okay, so this is Z Thevenin, where the real part is denoted by R Thevenin and the reactance is denoted by X Thevenin. And this is the Thevenin voltage. Okay, so we're talking about impedances. Clearly, this is a phasor domain circuit. So, in this scenario, suppose that this load impedance is our design parameter, and there's nothing that we can do regarding the circuit that this load is connected to. So that means V Thevenin and Z Thevenin are fixed, whereas RL and XL, the resistance and the reactance of our load impedance or the load, are our design parameters. And the question is, or the problem is, how RL and XL should be chosen so that the real power extracted by the impedance or the load L is as high as possible. Okay. So, to summarize, we have the following fixed quantities, V Thevenin and Z Thevenin, and the design variables are RL and XL, or in short, this complex number, the load impedance, ZL. And the problem is, or what we want to achieve is maximize the real power, okay, the average power consumed by the load, ZL. Okay, so let's call this current IL, the load current, the phasor of the load current. So this is what we want to maximize, PL. PL is effective value of the load current square times the real part of the load impedance, which is RL. Okay. In terms of the magnitude of IL, we can write 1/2 IL square, so that equals IL effective square, times the real part of the impedance, which is RL. Okay, so that's what we want to maximize. So let's express IL in terms of everything else. What's IL? IL equals the Thevenin voltage divided by the equivalent impedance seen by the source, which is Z Thevenin plus ZL, because they're connected in series. So that can be written as R Thevenin plus RL plus JX Thevenin plus Thevenin load reactance XL. Okay. Therefore, PL equals 1/2 times the magnitude of that fraction IL, which is the magnitude of the numerator divided by the magnitude of the denominator. And that can be written as, because we're squaring that magnitude, okay, we Thevenin magnitude square divided by the magnitude square of the denominator, which is real part square plus the imaginary part square. R Thevenin plus RL square plus X Thevenin plus XL squared. Okay, so that's IL magnitude square, and with that we're multiplying RL. So here we also have an RL in the numerator. Okay, so in this expression, V Thevenin is fixed and Z Thevenin is fixed. Z Thevenin fixed means R Thevenin and X Thevenin are fixed. So there are two things that we can play with, RL and XL. And by playing with them, we want to make this quantity as large as possible. Okay. Now, the denominator is always positive. Okay. And since we want to maximize this, we want to minimize the denominator. Okay. Of course, by playing with RL also appears in the numerator. So how to choose RL at this point is not clear, but since XL does not appear in the numerator, it can be chosen to equal, and we can choose any sign we want. It can be chosen to equal in magnitude X Thevenin and opposite in sign, so that this term can be made 0. Okay, so that seems like a reasonable first step. So let's put that down. Note that the term which is never negative, X Thevenin plus XL square, can be eliminated. Okay. Excuse me. Can be eliminated by choosing XL equals minus X Thevenin. By letting XL, the load reactance, equals minus the Thevenin reactance, X Thevenin. Okay. So once the choice regarding XL is made, now what remains is how to choose RL, and the expression after choosing XL equals minus X Thevenin becomes simpler. Okay, and we can write as the following. Okay. Then dPL DRL evaluated at XL equals minus X Thevenin. So by this choice, X load equals minus X Thevenin, this term disappears and the power equals 1/2 V Thevenin square times RL over R Thevenin plus RL square. Okay, so the only dependence now is on RL. How to figure out how to choose RL? What we do is, because it's not obvious, okay, what we do is we differentiate it with respect to our now only design variable RL, because XL is already chosen, and then equate the derivative to 0. We know that whenever the derivative is 0, we're either at the minimum or maximum, and in this case, this will give us the maximum for PL. Okay, evaluating this derivative, we have V Thevenin magnitude square. We can take it outside differentiation, and we differentiate with respect to RL over R Thevenin plus RL square, and equate this to 0, and this yields RL should be chosen equal to R Thevenin. Okay, so what we have obtained, therefore, is something that's very easy to remember. What you do is, when the load impedance is your design parameter to maximize the power, what you do is you choose the real part of the load equals the real part of the Thevenin impedance, and the imaginary part of the load impedance to the minus the imaginary part of the Thevenin impedance. Those two statements can be combined to the following very simple statement. To maximize the power, choose the load impedance such that it equals the complex conjugate of the Thevenin impedance. Okay. So that's a very elegant conclusion. Therefore, load impedance should be chosen to equal the conjugate of the Thevenin impedance for maximum power transfer for our case, where the load impedance is the design parameter. Okay, for our case. Now there are some other possible scenarios where the load impedance is not directly, we cannot play with it directly. We have to have some other choices to make to maximize the power. Okay, so let's therefore very briefly talk about them too. How about different cases? Okay. So what we did here is possible to generalize in some sense. So when the design variable is different, okay, what you do is you formulate PL, so that's what we want to maximize, in terms of design parameter. Okay. The design parameter, say alpha, and in a sense we had alpha here as RL, but before that we had to observe that we have to choose XL equals minus X Thevenin. Okay. Once that choice is made, our problem has reduced to maximization with respect to a single variable. And when you have that case, maximization with respect to a single variable, this seems to be a nice way to go. You differentiate it and equate the derivative to 0. Say alpha, then solve for d over d alpha PL expressed in terms of alpha equals 0 to find the maximum point, if there is one. Here's an exercise where you can apply this idea. Consider the following case. Again, we have some circuit that our load is connected to, okay? And that circuit has a Thevenin representation. V Thevenin and Z Thevenin, okay? Now, this is connected to our load, and for some reason we cannot play with our load as we were able to in the previous case. That is, we cannot separately play with the real part and the imaginary part, okay? Suppose that our load is a closed box and we cannot open that box. But what we have is, we have in our disposal, let's say, a transformer, okay? And we can connect one end of the transformer to the circuit and the other end to our load. Okay. Suppose the turns ratio is n to 1. And if this is the case, that is, we cannot play with the real and imaginary parts separately of our load impedance, but instead we can play with its magnitude as seen from the circuit through this transformer. Now this becomes another maximization problem, okay? So in this case we have the following quantities as fixed. V Thevenin is fixed, Z Thevenin is fixed, due to the obvious reason that we cannot interfere with the circuit that our load is connected to. Okay, that's a very reasonable assumption. And then in this case that I want to emphasize, we cannot also get inside our load impedance. So ZL is a closed box. So ZL is also fixed. But the ZL, the load as seen from the circuit, we can play with in the sense that by choosing the turns ratio, or by playing with the turns ratio, we can play with the magnitude of the load impedance seen from the circuit side. Okay, so that is, in this case, the design variable is the turns ratio of our transformer. And now the question becomes how to choose the turns ratio n so that the maximum power is extracted by the load from the rest of the circuit. So find n for maximum power extraction, PL. Okay, it's a very nice problem. For those of you who have time, I recommend that you work on it, and let me provide you the answer. The answer is n should be chosen so that it equals the ratio of magnitude of Z Thevenin to magnitude of ZL, then you take the square root. Okay, or n squared must equal the ratios of the magnitudes, Z Thevenin magnitude over ZL magnitude. Okay, now let's move on to another example where we can apply our finding in the previous case. Namely, the load impedance is chosen to make the chosen as the complex conjugate of the Thevenin impedance to make the power transfer maximum. Okay, so this is the circuit that we will study. RL 10 ohms, so that's the load resistance, and CL is 100 microfarads. This resistor here is 1 ohm, and this inductance is 2 millihenries, and here we have 100 ohms. This is the source voltage, and we have two sets of transformers. The ratio is given as N1 to N2 for this one, and N3 to N4 for the other one. Now, the story of this problem is that RL and CL, the resistance and the capacitance values, are chosen such that maximum power is extracted from the rest of the circuit. From the rest of the circuit by RL. Okay. At the frequency of 1000 radians per second. Omega 1000 radians per second. If that's the case, and we direct the given optimal values for RL and CL, what we're asked is we're asked for the turns ratios N1 over N2 and N3 over N4. Find the turns ratios of the transformers. Okay, so what we have to do is we have to simplify this circuit first after transforming it to the phasor domain. And once the circuit reduces to the topology that we have studied maximum power transfer problem, then it will be straightforward to figure out the turns ratios, which are what we are asked. So the first step is therefore transforming this time domain circuit to phasor domain. Not that we have everything we need. We have the parameter values, and also we have the frequency of oscillations, omega. So the phasor domain circuit is as follows. Okay, this is the source, 100 ohms. N1 to N2, N3 to N4. Okay, let's figure out the impedances. 1 ohm is 1 ohm in phasor domain. The impedance of the inductor is J omega L. Okay, L is 2 times 10 to the minus 3. Omega is 10 to the 3. Therefore, we have J2 ohms for the inductor. RL is 10 ohms, and as for the impedance of the capacitor, we have 1 over J omega C ohms, and that produces JXL equals minus J 10 ohms. Okay. Okay, so let's obtain the circuit, or the Thevenin equivalent circuit, seen by our load, okay, from this pair of terminals. Look to the toward left. First, let's deal with one transformer at a time. First, deal with this transformer. That is, let's replace this thing here by its Thevenin equivalent. Okay, If you do that, this is what you obtain. Here we have Vs, and here we have the resistor. Okay, to find this voltage, we're talking about Thevenin equivalent circuit, see from this pair of terminals. What you do is you compute the open circuit voltage. It's simply Vs raised according to this ratio. Okay, so what we have is N2 over N1 Vs. To find the input, to find the Thevenin impedance, kill the source, and then this 100 ohms transferred to the other side by N2 over N1 square. Hence we have N2 over N1 square times 100 ohms, okay, for this resistor. And this thing here is the Thevenin equivalent, see from this pair of terminals. And then we have the rest of the circuit. 1 ohm, J2 ohms, and we reach the other transformer. Okay, N3 and 4. And let's do this transformation once again, this time to the other transformer. And after that step, we will have obtained the Thevenin equivalent circuit seen by the load impedance. And then, since the load impedance must be the complex conjugate of the Thevenin impedance, we will be able to figure out the turns ratio N2 over N1 and 4 over N3. Okay, so that is equivalent to the following circuit. Okay, this is our load impedance ZL, which is 10 minus J10 ohms. And then here we have the Thevenin voltage N2 over N1. Here we had N2 over N1 Vs, and then this transformer plays with it once again. And what we have is times N4 over N3, and then we have Vs. So that's the Thevenin voltage. Okay, what else? This is our V Thevenin. As for Z Thevenin, which is represented by this box here, what we have here is kill this source, replace it with short circuit. Here we have the impedance of this plus that, and that impedance is transferred to the other side proportional to by the factor of N4 over N3 squared. So therefore Z Thevenin equals what? N4 over N3 squared times this whole thing here, which is 1 plus N2 over N1 squared times 100 and plus J2 ohms. Okay, so we have just obtained in the beginning of our lecture that for maximum power, when we can play both real and imaginary parts of the impedance, load impedance, ZL should be chosen as equal to the conjugate of the Thevenin impedance, Z Thevenin. Okay, ZL must be chosen to equal Z Thevenin star. Therefore, ZL is 10 minus J10, and this must equal therefore this thing conjugated. Okay. Okay, so we have therefore n 4 over n3 square 1 plus n2 over n1 square 100 minus j n 4 over n3 squared times 2. This is our ZL, and this thing here is our Z Thevenin conjugate. Okay, we have two unknowns, n4 over n3 and n2 over n1, and we have two equations because this is a complex equation. By equating real parts and also the imaginary parts, we solve for what we're asked for. So let's do that. So that's the imaginary part, n4 over n3 squared times 2, that must equal 10. Okay, then that gives you the terms, one of the terms ratios, n4 over n3 squared times 2 equals 10. Okay, so that means n4 over n3 must be square root of 5. Okay. As for the other terms ratio, we look at the real parts. 10 must equal this thing here. What we have therefore is n4 over n3 squared, which is 5 times 1 plus n2 over n1 squared times 100 must be the real part of our load impedance, which is 10. Okay, so this square is 5, therefore this thing must be 2, remove 1, therefore this must be 1, therefore n2 over n1 must be 1 over 10. 1 plus n2 over n1 square equals times 100 equals 2, which yields n2 over n1 equals 1 over 10. Okay, so those are the turns ratios. Okay, let's see now another example, not necessarily related to power, maximum power transfer, but still it has to do with power, complex power. Okay. Consider the following simple topology, and the circuit is given directly in phasor domain. Okay. This is Vs. This here is the current labeled as Is. The impedance of the capacitor is given as minus J20 ohms. Here we have J20 ohms for the impedance of the inductor, and the resistance is 20 ohms. This voltage is labeled as V0, or the output voltage. Now, we're told that the average power delivered to the resistor is 500 watts. Okay. If that is the case, we're asked for the following quantities. Find the effective value of the output voltage, V out RMS. Find IS RMS. Find effective source voltage, VS RMS. And finally, PF seen by the source. Okay, so let's proceed through complex powers, remembering the fact that complex power is conserved throughout the circuit. Okay, this is not the only way to go, but seems to be the quickest and simplest way to solve this problem. So the complex power associated to the resistor, 20 ohm resistor, is the square of the effective value of the voltage across the terminals divided by the conjugate of the impedance of the component. Now, ZR conjugate. Now, since ZR is real, 20 ohm, its conjugate equals itself. So ZR conjugate, in our case, is 20 ohms. And as for SR, okay, the complex power, the real power is 500 watts. This is a resistor, okay, therefore it will have no reactive power. Its voltage and current are in phase. Therefore, its complex power is 500 plus J0 volt amps. Okay. From that equation, we immediately obtain the RMS value of the voltage. Okay, V out RMS square equals 10,000. Therefore, V out RMS equals 100 volts. Okay, so that voltage is also, because the two components are parallel, is the voltage of the inductor here, okay, whose impedance is J20 ohms. So that will be our next component of study, SL, the complex power associated to the inductor, okay, with impedance J20, equals the square of the effective value of the voltage of the inductor divided by the impedance conjugate of the inductor. Okay, ZL conjugate, and that's 10 to the 4. Okay, 10,000 for the voltage square, and ZL is J20, therefore its conjugate is minus J20, and that produces J500 volt amps. So that's the complex power of the inductor. And then once we have the complex power of this and that, due to conservation of complex power, the complex power delivered to this, considered as a single load, must be the complex power of the inductor plus the complex power of the resistor. Okay, and once we know the complex power, we also know the effective value of the voltage. We can compute the apparent power, and dividing that apparent power by the effective value of the voltage will give us the effective value of the current. Okay, so IS RMS therefore equals the apparent power of this combination, which is SR plus SL magnitude over the voltage, RMS value of the voltage, V out RMS. So that equals 500 plus J 500 magnitude, which is 500 times square root of 2 divided by 100. That produces IS RMS equals 5 times square root of 2 amps. Okay, so this is computed, this is computed. Let's figure out Vs RMS. Okay, now the complex power of the inductor and the resistor is computed. We also know the RMS value of the current passing through the capacitor. Therefore, we can compute the complex power of the capacitor, which is RMS value of the current squared times the impedance of the capacitor, which is here. Once that complex power is computed, we can write down the complex power of the whole thing considered as a single load. Due to the conservation of complex power, the complex power delivered by the source must equal, okay, the complex power of the capacitor plus complex power of the inductor plus the complex power of the resistor. Okay, once that complex power is known, automatically its magnitude is known too, and namely the apparent power delivered by the source, and then apparent power divided by the effective value of the source current will give us what? Vs RMS. Also, from the complex power information, we can easily obtain the power triangle, and the power triangle will give us the power factor seen by the load, seen by the source. Okay, so let's complete therefore this problem. Okay, now SC, the complex power of the capacitor, equals IS RMS square times the impedance of the capacitor, which is minus J20 times 5 square root of 2 square, because IS RMS was computed in the previous step. And that produces minus J1000 volt amps. So that's RSC. Then Vs RMS equals the apparent power supplied by the source divided by the current, effective value of the current leaving the source. Okay. So what we have is SR plus SL plus SC. Due to conservation of power, this sum must equal the complex power supplied by the source divided by IS RMS. So that reads 500 minus J500 divided by 5 square root of 2, which produces Vs RMS equals 100 volts. Okay, and finally, complex power supplied by the source SS, let's call it, equals SR plus SL plus SC, which is here 500 minus J5. J500, okay, volt amps. Okay, so that's the complex power supplied by the source. So that means we have the following power triangle. Okay, here we have what? Minus 500 volt amp reactive. Here we have 500 watts representing the real power. And this hypotenuse is 500 square root of 2. That's the apparent power. Units, volt amps. And here we're after this, the cosine of this angle. Okay. So PF equals cosine, let's call it phi s, cosine phi s. This is clearly 45 degrees, so that's 1 over square root of 2. So that's the cosine of 45 degrees, pi over 4 radians. Now, as for this power factor, we have to also specify whether it's leading or lagging. For that, we look at the sign of the reactive power. If it's positive, it's lagging. Okay, if it's negative, it's leading. In our case, it's negative. Therefore, the power factor of the source equals 1 over square root of 2, comma, leading.